Going live. Hopefully we're live. There we go. Boom. Hey, it's me. Hello. And welcome to Practicalli. Thank you very much for joining me on this chilly November day. Hopefully you will enjoy today. So we're going to cover, what are we going to do today? We're going to do some more exorcism challenges, and we're going to do one called bank account. And that, solving that is asking us to do something that's thread safe. So we're going to use atoms, and we'll have a quick look at refs as well, and basically using Clojure's Software Transactional Memory, and explain what that is. Okay, quick advert. So if you want to catch up with anything on Practicalli, it's on the website. And so you can go in there and catch up what I've been doing, improvements I've been doing, thanks to the Clojure Together sponsorship. So all the broadcasts, all the books, and I've been doing some more stuff on Practicalli Spacemacs to show you how to use the documentation in there as well. Some other neat things. I studied a data science book. It's very minimal at the moment. It's just got some things around this project called Notespace, which is a really nice little journal for data science, and you can display your content in there. And I've got it. I'll show you how to walk through setting up that project, and also launching Notespace and Portal, which is a nice data browser. Just launching them at when you start up a REPL, and that's regardless of whatever REPL tool that you actually use. If you want to reach out to me, you can use all these channels. I'm mainly on Zulip and Slack, but also trying out Discord as well. And then you can support me in these channels as well. And thanks to everybody that does support and continue to support me on there as well. It gives me more time to work on the books and the rest of the content as well. Okay, bank account. Let's go on to the meat of today. So we are doing the exorcism challenge called bank account. And what is it asking us to do? Well, we're trying to simulate a bank account. I think this is a very simple bank account. We've only got open and closing and withdrawals and deposits of money, but want to watch out for concurrent transactions. So I want two things happening at the same time. And normally we could get our database to manage a lot of this in what it calls an atomic way, so that only one thing is updated at once. And this would help us to be able to access a bank account in multiple ways. It's a bit hard to submit a database to exorcism. So luckily Clojure has this built-in software transactional memory. So if we go to the internet and do Clojure software transactional memory, there's a section on concurrent programming and refs and transactions in here, which goes in and explains one of the real kind of invaluable things about Clojure is it can just make doing thread safe concurrent coding really simple. And so we've got this idea of software transactional memory, which is essentially like having an atomic database inside your REPL, inside the running memory of your program. And Clojure manages that by only allowing you to change the information inside the software transactional memory one thing at a time. So if you've got lots of different threads trying to update the atom, they're all going to have to take in turn. So you don't have to worry about doing any locking and managing that. It's the software transactional memory is taking care of that for you. I guess I kind of equate it, although it's a different kind of aspect, I equate it to kind of like Java does garbage collection, so you don't actually have to go and clean up your code, clean up your memory usage, because Java is taking care of that for you. So it abstracts all that away from you. So that's the difference between Java and C, C++, where you have to do the memory management yourself. With Clojure, then Software Transactional Memory helps you just manage changing of values. And so yeah, you don't have to worry about locking and unlocking stuff and all that. All the joys of concurrency are kind of managed for you by Clojure. And so there's some examples here. Some very big examples here. We're going to do some lot simpler stuff than this, I think. There we go. And we could use refs, but we're going to start off by using atoms, which are a much simpler thing to use as well. So we'll have a look at that. Let's just check what else we need to do. So bank accounts can be accessed in multiple ways, making deposits, blah, blah, blah. Yes, we've done that. It should be possible to close an account as well. So if we have a look at the test suite, then we've got a fixture here which is shutting down agents. So what is this doing? So you can see it's doing multiple kind of things in between these tests. So these tests aren't just a single call. Oh, and it's doing a parallel call by the looks of it. Usually when you put P with something in a name of a function, it means it's doing parallel calls for that as well. So here it's trying to add 10 to the bank account, I think. Oh yeah, so here we're doing update balance account with 10. And so with software transactional memory, then all of these would be added in turn, so they wouldn't conflict with each other. Okay, well, I've downloaded this already. So I've got the bank account thing downloaded via the exorcism command line. So it's created a skeleton for me, and I've created this design journal file to do some experiments in, and all our tests are in here. Whee, there we go. Oh, boom, boom. And yeah, and then our skeleton is, so we've got skeleton code, so we've got bank account. Oh, they've already given us an atom to work with, so that gives you a nice big clue about where to start. And then it's, oh, actually no, oh, that's completed code. Oh yes, I've already done that, sorry. Yes. So we're going to walk through this solution and show you how we did that. Okay. Oh, I can't spell today. There we go. Boop. Oh, maybe not. It doesn't like the word transaction on my spell checker. I'll have to add that. Okay, so in Clojure, you may have noticed that everything is immutable by default, which makes things nice and simple. So if we define a map, then the map is the map. We can't change the map once we've defined it. Although we can, when we're coding, we can actually just redefine the names we're using to represent that that map, but we're not actually changing the map itself. So if we do, if we evaluate this, this creates a name called Design Journal Me, which when we evaluate that, it shows that that's the value that me points to. And so we can, when we're programming, we can go in and change the names of things and the values that me points to. But this is very much a development time change. I'm not doing that when the program is running. But if I want to change the map, what I'm actually doing is if I do something to the map, if we do our sock, so our sock will take some map and then you can pass it a key value or lots of key value pairs, and it will basically put in the new values into the map. But this is returning a new map. So if we are sock me age 42. Oops, I pressed the wrong button there. I keep doing that. Yep. Then we get a map and it looks like it's changed. But if we actually just go in and evaluate me again, it's still the original value. So we haven't actually changed me. Although when we actually run the ASOC, it looks like we've changed it. In fact, this is just a new copy, and whenever we work with values and we create a copy, we return a copy of that value. And if it's a big value, then there are structural sharing inside there. So we do so in an efficient way. So we're not duplicating everything in the memory. We're only creating new things that are different. So what happens if we actually do want to change something? That there is obviously value in changing things. Eventually, the world isn't static, and so obviously we can put things into databases, and databases are designed to kind of change. Either relational databases just have a snapshot of the current kind of information, or you can have something like Datomic, which does time-based transactions. So you can see data evolving over time. But really simple approach is just you can always think of Atom as a very kind of minimal database that you've got inside the memory of your computer. And we can just take our original value, and wrap it with an atom. And so, yeah, so we got here, oops. So we put an atom in there, and instead of just creating a value, it's like a wrapper around the value, and so it's like a little container, a little box you get from your favorite online store. Brings you a box, and it's got something in it, and you order like 6 things. They're all kind of in the same kind of box, but inside the box they're all the things are different. And we can give that a name so we can refer to it. So if we define state to be an atom with some value, then we can call state by itself. Oops, that's not the right one. And we get the atom back. So again, we're referring to the atom. We're not getting the value that the atom contains. We're getting the atom itself. So if we actually want the name, we actually use the deref function, and this says, goes to the atom, says, hello atom, I'd like to have your current contents. And so it returns the hash map that is the value that the atom is managing for us. And there is a shortcut which is more commonly used. I don't see deref actually used that much because it's much easier to just use the at state. And we do and that returns the same value. So that's giving us the value that the atom is managing for us. So that's the same as the line above. So that's returning the, pardon me, oops, wrong one. So those both return the same value. And because we're managing this value with atom, then we need to change the way we change the atom is going to be different as well. So we need to use different functions. We can't just use assoc because we're talking to an atom. We're not talking to the map directly. So we're not talking to the hash map directly. So we've got things like swap and reset to use. Let's get rid of, oops. Oh, we're doing. There we go. So if we want to create a new value in the atom, then we can use swap. So basically swap is just swapping the existing value for the for a new value. Swap. And then so this takes an atom and a function, or an atom and a function and a value. So we're going to take states, and then we want a function. So we do assoc. Then name, age 42. Oops, did I get that wrong? Oh, I messed up. It's been a while. I spelled the spelled that wrong. There we go. Excellent. I can program. Yay. There we go. So when we now go and deref state, let's just use that for now. Now we get the updated value. So although the original value that we put into the atom was immutable, name Johnny, we've actually got now a new value in the atom. And at first I thought that this was actually changing, the atom was changing the value, so it was actually breaking the immutability of the underlying value. But actually it's not. I mean, the clue is in the name of this function we've just used. The function is called swap. It's not called change. So it's actually swapping the original value for a new value that it's creating. It's taking the original value of state, and then it's using the assoc function to update the value. So creating a new value using the assoc and adding in the two extra values, and then we get a new hash map that is then the value that is managed by the atom. Another one we can do is do reset. So we can just do reset. State. Let's spell it right this time. There we go. And so if we look down at the bottom here, it's just showing us that we just give an atom and just passing in a new value. So literally we are just resetting the value. So we're going to reset the value to this, to original state. And so before we run that, then obviously this is name and age value in the map. And if we run this, then it's going to be just the name again. And so when we call deref, then we're back to what seems to be the original value, but actually it's yet again a new value that we've created to put in there. And so again, so the atom is helping us manage that. And we can use assoc and assoc in. We can also do updates. The difference between assoc and update is that associate is kind of adding or replacing values in a map that the atom is managing, where update is going to actually take the original value and update it with a function. And when we're coding, we might want to have a start state for the atom as well. So when we define an atom, so we can use def, or we can use def once. And if we use def once, then this is reload safe code. So if we reload our code in the REPL, the atom isn't going to be reset each time. So if we want to reload our coding because we've made some changes, but we want to keep our state, then if we use def once, then it's not going to redefine the state like halfway through we're running our code. If we make a change and we want to reload the new code in, we'll still keep our original state because this atom won't be reset to this value. So sometimes you'll just define atom as an empty kind of collection, and then you'll use that to just so you've got an atom in place, and then you'll share that between all your functions that you're actually using. Hopefully that makes sense. Where are we going? Any questions? No questions so far. Okay, so let's look at our code. Oops, wrong window. There we go. So for the bank account, I've just done this def once bank account atom, and so we're going to use a map to hold the account name and the kind of account IDs and so on, and like the current balance and so on. So when we open a bank account, then we can create account ID, and here I'm just using a Java util function called UUID random ID. So it's in Java there's a UUID class with a method called random UUID, which generates a random universal ID for us. So this is using Java interop, and because it's in Java util, I don't think, we don't need to include that. We don't need to import anything. It's just using Java out of the box. It's included in like the Clojure runtime, and so we're just binding that to account ID. So this helps us generate unique IDs for the bank accounts without having to do any kind of real effort. It's a nice simple way to do that. If you're actually using this for a real database, then potentially there's some indexing options. If you've got a lot of account IDs and you're using random IDs, it's much harder to build an efficient index, but we don't have to worry about that kind of thing because we're just using the atom. And then, like before, we're taking the bank account atom, so the one we've defined here, and we're going to associate in the account ID of with a value of 0. So the account ID is the UUID we just created, and yeah. Boop. Oh, what did I do there? What's that not working? Oh, banking. I didn't evaluate the bank accounts. Oops. There we go. And then we can do the same thing for if we want to close the account. That's really simple as well. So basically we can just take, if we're given the account ID, we can just use disassociate, which is kind of the opposite version of ASOC. So ASOC is adding a key to a hash map, and disassociate is removing that key from the hash map. So if we've got disoc, we can, when we've just got a normal hash map, which way around does this go? Oh yes, it goes that way, surely. Yeah, so this goes map and key. So if we disassociate the name key, then we get an empty hash map because there's no more keys left in there. We've removed the key, and because we're removing the key, then we're removing the value that's associated with the key as well, because they're very much a key value pair inside the hash map. And then to get the balance, that's really easy. The only difference, because we're using an atom, is we can use get to access the hash map, but in order to get the hash map, we dereference the bank account, and we've given the account ID as the argument, so we can just use the account ID as the key to look up in bank accounts the value of the account. And then we want to update the balance. Then we can, we're given the account ID again, and the credit, so how much we want to change the balance by. And we can then again just do a swap. This time we're using a little function in here to take the previous balance and add it to the credit. So basically taking in, so when we're doing update will receive the value from account ID. It'll get that value from the bank accounts map. So we'll know, we'll have that value, and that's passed in as an argument, and we're calling that argument previous balance. And then we're taking that balance, just adding the credit that's passed in as an argument here, and we get our new balance. Rather than using the full form, we could actually just use, if I do space k raise r, and then we put a little hash on there. Boop. Now we got the short form of the anonymous function, and if we just change that to %, there we go. Oops. I think we stick it all in one line, and then that's, yeah, that's probably a good example of using the shorthand syntax for an anonymous function, because it's doing something very simple and it's just all in line. Yeah, we're just adding the original value from update with the credit value that we get from an argument. And there we go. And it still compiles. Yay, there for me. Good for me. do the tests run? Dare we run the tests? Let's see. Let's see. Oh yeah, okay. Oops, bank account. Tests. Bank account tests. So these are the tests that come with exorcism. I haven't changed them, I don't think. Oh, I was having a little play with that. Okay, so let's run the tests. Keep my fingers crossed. Oh, my REPL's broken. That's not good. How bizarre. I've broken it completely now. Oh, have I killed Emacs? What's going on? Oh no, it's there. There we go. I'm not sure what happened there. Oh. Let's try that again. I haven't added I'll add a deps.edn file to this as well, so you can run this with Clojure CLI tools as well. I don't want to run my dead REPL. I'll hopefully use a new REPL connection. Okay, so now I'll need to go back and just evaluate this buffer. I don't think there's anything else in here. Oh, actually, I should put this into. Oh, that's my design journal, isn't it? Oops. Let's open the real file. That's why I couldn't find it. Yes, so let's here. So this is our hopefully working solution, which is just the same. I don't think I did anything different here. No, yeah. I've just got some code here that tests. I just did some tests here just to make sure we can see what it's doing. I think that's all commented out. Yes, it is. So this is before I started using the rich comment blocks. You can just do individual, just using the reader macro to comment out individual lines, individual expressions, as it were. So it should be able to just evaluate the buffer, and it just loads the code that's not commented out. There we go. So we can do open account. That doesn't take any arguments, so we can call this end of file while reading. Why is that not doing that? I used to be able to do that. Just there you go. So if we open an account, we get back the UUID. So that's what I'm doing here. So we're swapping the bank account value. We're basically adding a new bank account by creating a new key in the map, and I'm just returning the account ID that I created, just so I've got that bank account ID, which is useful. So it's very much like if you created this in a database. It's quite usual, quite common to get back the value of any kind of automatically generated value. So if you're using identity or some kind of random UUID generator, then it'll, when you've done that SQL statement, it'll return the new value. So you've got the account ID that you created. Otherwise, how do you know how to reference that account? I just did some little tests here, but let's see if we can just run all of our tests. And so, yeah, so we've got the only thing different I think we've added to this is we're using a fixture in here. So this fixture will run once. So when we start running our tests, this fixture above here is going to run once, and then at the end of running all the tests, it's done. You can do it every, and that would run the fixture for every thing here. We're just doing some shutdown. What does that do? Yeah. Oh yeah, so this is shutdown agents is a Clojure core function, and it's just initiating a shutdown for all the thread pools. So we're using an agent, which is another aspect of software transactional memory, to actually just generate the different threads. And so we're basically just making sure we're cleaning up after ourselves after we run a test. Otherwise, we'd have lots of threads just hanging around. So let's try running the tests. Oh, it doesn't seem to like running the tests. That's not good. Oh, that's terrible. Oh, that's killing. That's killing that. Oh, that's interesting. I can't seem to run the tests because they just keep breaking. I'm not sure if that's the Cider test runner or if it's something in the version of Java I've got. Well, that's something I'm going to have to fix, I think. But we can kind of use these little experiments. Yeah, there's a question about, do we need the shutdown agent stuff if we're implementing this without using agents? What we could do, actually, yeah, I think it's because, is this using agents? Boom, boom, boom. No. Yeah, I'm not sure why that's using that. It might be, is it because of P calls? Oh, yeah. It's blown my Clojure up. Blown my Clojure REPL up. Let's start it again. No, I don't want to reuse it. So when you first start Cider, you just need to evaluate a namespace to load all the the Clojure core information in. So now we can use h, HH to look at it. That doesn't say an awful lot. We can go and browse the code. And that uses pmap. We're going around, we're going further into the rabbit hole. What is that doing? It's like map, but using a function in parallel. Let's go and have a look at pmap. I'm trying to see where it's actually using agents, if anywhere. That's interesting. That's something to go and have a look at, I think. Probably in another session, otherwise we'll be here all day. Oops. Didn't want to do that. I wonder if I could just, what happens if I get rid of the fixtures? So if I comment this out, then it shouldn't run the fixtures at all, just to see if it's the fixtures that's actually breaking it. Yeah, it might use the 3. So this might be a bad idea, but it might help the test to actually run at least once. But I can't guarantee that. Hey, there we go. So I've no idea what it's done to the state of my my REPL because I'm not cleaning up afterwards. But it's run the test just by essentially disabling the fixtures. I can now run the tests, and they all run successfully. So that's an interesting thing to do. So yeah, so investigating why shutdown agents is breaking the tests. That's an interesting one. I have to add a note to that on. Might be worth adding a. I'll try adding a deps.edn file, and I can run an external file for an external test runner. let's see, let's do bank account deps.edn. Let's just add a very simple paths. Let's do source. Let's be naughty and just stick test in there as well, just in case we don't need test. But the we do need that for the cider test runner. But what I can do now, I've got that. Now we can run this REPL here. Well, we can run REPL as a using the Clojure CLI tools. But it means we can also use some external Clojure CLI tool that I've got set up. See if I do. So I'm in bank account. If I do Clojure -m, I do have a test runner, I think. But before I do that, I want to change back to fixtures, put the fixtures back in, and let's see if test runner runs. So I think this is, I can't remember if this is using the Cognitex lab. I think it's using Clojure. So this will run the tests. Oh, and that works. Yeah, so this is oh, okay, so that's interesting. So it's seems to be something, for my very lack of exhaustive testing, it does seem to be something specific to the cider test runner. Because if I'm using this external Clojure test runner, then all the tests are actually working. That's with the fixtures there, because I did save the file. Yes, I did. So that's interesting. Well, that was an unexpected journey. There we go. So it is useful if you do have issues with your editor, the way your editor is working. It's always useful to go back to, effectively what I was doing is going back to the command line and just running running an external test runner that I've got set up here. So if we do GitHub Practicalli Clojure deps.edn here, so because I'm using Clojure deps.edn, I've got all these test runners that you can use. Whoops, where's the index gone? Oh, there we go. So we've got a whole bunch of test runners, and so we've got test runner is just running Clojure by default, but then there's lots of different, and it also includes the test path in there as well. But there's other ones as well. There's the Cognitex Labs and Midge and EFTest and Cloverage, which does some coverage there as well. Cool. Okay. Anything else we want to cover? I think I'll leave. Oh, there is a quick example of refs. We can just go and have a quick look at that. I think. Did I create that? I think I created a refs version. Yeah. So we can use, rather than using Atom, we're using a ref here. And so refs are designed to be able to update multiple values. So if we've got multiple things that we want to update at the same time, then we can use a ref instead of an Atom. But it's pretty much the same thing, except we're like using this in the wrapped around a do-sync, which is kind of like a try block for software transactional memory, really. And we can do multiple things here, but in this example, we're not actually updating multiple. We're not updating different accounts at the same time. We're updating the same account multiple times. So for that, an Atom is perfectly. It's probably the right choice. And even with an Atom here, if we wanted to update multiple accounts, then we could just do that in the swap file. We could actually just update multiple keys in the map. So just have all our accounts in one big map, one big hash map, and then we can still use an atom and still update, can still do a transaction from one account to another by just updating two different keys at the same time, and they'll both have to change within the swap, or they'll both be rolled back if they don't change, and they both happen at the same time. So it can't be affected by anything else. One can't be affected by the other because they're just happening at the same time. So I think generally just using an atom will do 99% of all the kind of software transactional memory things you want to do, and then only if an atom isn't up to the job, then you can start looking at refs and maybe agents as well. That seems to be the collective wisdom of the Clojure community for what I've gained. And there is I do have another example. If we go to, where is it there? No, that's not it. There we go. Just close these down. Note. Oh, there we go. That's the one. So I've got a Clojure through code project, and then there's one called changing state, which goes through some examples of using some atoms here, so using swap and so on. And then there's also like an example of a card game. One of the interesting things you can use things like validators on there. So here we're putting basically putting a conditional on the atom, saying that it can't have more than two values in there. So that means we're kind of limiting the players to 2. So we can only add 2 players. And if we try and add so if we're doing join game, we can add Rachel and Harriet, but when we try and join Terry, then because the validator condition, that stops us doing it, because otherwise there'd be too many players in there. Oh yeah, there's an example of kind of just updating accounts here, so you can kind of update multiple keys at the same time. So you can do that inside a swap as well. So that's how you would do that without needing a ref to update multiple accounts. So obviously, if one person wins, so like if Jenny wins, they'd get money, and then the dealer would lose some money, and everybody else would lose some money. So you could update all of those keys at once with the changes that are required. And I did put in a refs example as well, but you can do that. I would probably just do that as an atom and just have and just have all these individual defs, just have that as a single hash map. Yes, that's something else to add to the book, I think. I don't think I have a section on software transactional memory, so I'll use these examples to write that in the next week or so. Cool. Okay, I'm going to leave it there. I think hopefully that's given you a nice insight into software transactional memory. I got very confused with it at first, but when you just start using the atom and experimenting with the atom, it makes it a lot simpler just to kind of understand and see what it's doing, and using that in the REPL does help you do things like that. I'd be interested to see if there's any more little techniques you can do around that. That's quite a neat approach to putting a condition. It's like having a pre-condition on functions and so on, but for an atom. So that's quite nice. Okay, well, thank you everybody for joining. I hope you enjoyed that session, and my example of the bank account it can be seen in Exorcism. I'll also push that to the GitHub repository for all my Exorcism challenges as well. So feel free to reach out to me via the usual channels if you've got any questions, if you want to see anything in particular in these broadcasts. Always trying to wonder what would be interesting to show each week, so any kind of suggestions are always welcome. Okay, well, thank you very much, and see you all next time. Thank you. Bye-bye.